Okay, can you see my screen? All of you, can you see my screen? All right, perfect. Okay, so we are now in week 4. Okay, now we are in week 4. The topic that I want to discuss with you today is lecture 4, solidification. Okay, so for today's lesson, which is Tuesday and Friday, I'll be discussing on the understanding of solidification. Okay, I'll be discussing with you the understanding of solidification. Let me see. Okay. Okay, after this class, I'll be uploading tutorial 2 in Webble. So you can start practicing tutorial 2, which I'll be discussing with you on this coming Friday for group 2 and next week Friday for tutorial group 1. So that is the flow. Huh? Okay, now let's look at solidification. Now, as you know, material can exist in 3 different phases, right? One is solid, liquid, and gaseous state. Okay, material can exist in 3 different phases or coexist in 3 different phases, which is solid, liquid, and material. Oh yeah, thanks. Thank you very much. I need to record. Okay, thanks a lot for reminding. Tend to forget recording most of the time. Okay, thanks a lot. I'm recording now. All right. Okay, let me repeat again. So today I'm going to teach you the topic on solidification for week 4, which will be divided into 2 parts, which is today and also this coming Friday. Okay, so now in material, there is material can exist or coexist in 3 different types of phase. It can be either solid, okay, it can be either solid, it can be either liquid, or it can be gas. All right, now I'm going to concentrate on what is the understanding or what is the sign behind converting from liquid to solid. Okay, the science behind or the rationale behind the understanding of liquid to solid. Okay, all of you can listen, right? Okay, all right. Okay, that's good. Okay, now metals are melted to produce finished and semi-finished parts. Okay, so let's say for example, you have a solid rusty materials in a metal smith. So you melt a metal up to 1600 degrees Celsius, it becomes liquid metal. And then you pour those metal inside a mold and it becomes hardened. It turns from liquid to solid back again. So what happened in that process is a material in solid, all the atoms in solid gets sufficient energy to overcome the adjacent energies between atoms to release themselves to become free moving elements. So that is liquid phase. Okay, once it is in liquid phase, all the atoms are in excited stage where they move in a highly random manner. Okay, so there's another process, we call that as solidifications, where an atom releases energy to become in a more stable state, which is solid. Solid is always stable. Okay, we can call that as equilibrium state as well. So In order a material or atom to become solid, there are two steps involved. This is the one, highlight this. The first step is nucleation, and the second step is growth of nucleus into crystals and the formation of grain structure. Okay, the first step is nucleation. The second step is growth of nuclei into crystals and the formation of grain structure. Okay. Nucleation is the formation of stable nuclei in the melt. Okay. While the material is still in molten state, metal. Okay, let's talk about metal. Okay, I don't want to talk about material. Let's talk about metal. You can be more specific. Okay, once the metal is in liquid state, it is right above its solidifying temperature. So it is in liquid state. All the atoms tend to form a stable nuclei in the melt. Okay. Once the temperature decreases further, the atom releases energy and those nuclei will grow into crystals. Okay, those nuclei will grow into crystals and the crystal expand further to form a grain structure. So this is the flow to form a grain structure. So thermal grains, higher thermal gradient, different shape of grains. Lower thermal gradient, different shape of grains. So thermal gradient is the difference between highs and lows of a temperature in a material. Okay. All right, now. So this is what I mean by growth of nuclei. Okay, in liquid state, schematic illustration is showing several stages in solidification of metals. A over here, formation of nuclei into crystals. So you have nuclei here, and this nuclei will grow into crystals once the temperature reduces. Okay, then all these crystal joins together this boundary. Okay, you can see a boundary layer, right? Okay, this is the boundary layer. Okay, the boundary is huge. It grows and then those boundary layer becomes small, shrinks, and it forms a boundary layer. That is what we call as grain boundaries. So this crystal goes into grains from nuclei. Okay, let me repeat. In liquid metal state, nuclei starts to grow, and the growth of nuclei turn into crystals, and the growth of crystal turns into grains. Then you have your boundary layers, it becomes hardened. That's all. So the formation of nuclei, you have two types. Okay, two types of formation of nuclei. One is heterogeneous nuclei, another one is homogeneous nuclei. I will explain to you further on the difference of two and the principle behind these two types of nuclei. So nuclei grow into crystals mean nuclei align with each other. It is randomly until it becomes large enough to align into each other. Okay, it is in random, but once it is large enough, it aligns into each other to become a stable material, which is equilibrium. So the grain is made of crystal. Yes, the grain is made of crystals. Okay, Teo Chan Zan and Chin Wailuk. All right. Now, as you all are aware of, solidification process involves changes of phase, okay, from liquid state to solid state. Okay. For phase transformation that occur at constant temperature and pressure. Okay, let's talk about constant temperature and pressure. There's no change of there's no change in temperature. temperature and pressure. Now, there is an energy involved. We call that as Gibbs free energy. Okay, this is what I'm going to concentrate on this term, all right? The relative stability of a system is determined by Gibbs free energy. And Gibbs free energy is given in this equation. Okay, G is Gibbs free energy is equivalent to H is enthalpy minus Ts. T is your absolute temperature and S is entropy. Okay. All right. Nuclei only starts to grow to form when the melt cools down. Yes. When, not to say cools down, you can say when the energy is being reduced. Higher temperature, higher energy. When the temperature decreases, lower energy, atom excitation stops, and it starts to grow small particles of nuclei. Okay, Nur Harpinder, what Gibbs energy is used for? Okay, hold on, one by one. Okay, I just started with Gibbs energy. Gibbs energy used for you to calculate the exact amount of heat treatment required for a material. Okay, Gibbs energy is used for you to calculate the exact amount of heat treatment required for a metal. There are few types of relationship in Gibbs energy. Surface Gibbs energy, you have bulk volume Gibbs energy, and so on. I'll be discussing with you one by one, right? For today and also for Friday. Okay. So highlight these guys. G is equals to H minus Ts, and H is your enthalpy minus Ts. T is your absolute temperature and entropy. Okay, just focus on Gibbs energy. Enthalpy must be minus with your Ts, which is your absolute temperature times with your enthalpy. So enthalpy, enthalpy is the total heat content of a system. Okay, by now you should know after you have taken thermodynamics 1, enthalpy and entropy. Enthalpy is the total heat content of a system. All right, and entropy is the unused energy. It's properties. Okay, entropy is unused energy. It's a measure of unavailable energy in a system. Randomness, we can call that as randomness. So it is always a difference between enthalpy and entropy. All right. Now, enthalpy is a measurement, is a measure of heat content in a system. Okay, I've repeated that. H for enthalpy. So enthalpy is equivalent to the internal energy, which consists of kinetic energy and potential energy. Loa Wenzeng, yeah, I'm coughing. I don't know why. Okay, hope it doesn't transmit through the microphone. Okay. Thanks. All right, let's continue. Where am I? Okay, enthalpy is a measure of heat treatment content of a system where H is your enthalpy, is your internal energy. Internal energy is made of kinetic and potential energies. Highlight these. Kinetic and potential energies of atoms in the system. And PV is your pressure and volume on the system. Okay, let's imagine a closed system, right? All right. Transformation occurs when the heat is absorbed or evolved will depend on the rate of change of enthalpy and rate of change of pressure and volume. Okay, changes in enthalpy, internal energy, and also changes in the pressure and volume. So that is when the transformation will occur. Okay, heat is being absorbed or heat is being released. Is it exothermic reaction? Is it endothermic reaction? Okay. Now, condensed phase. Okay, condensed phase, example liquid and solid, your PV term is small in comparison to E. Okay, your internal energy is higher than the pressure and volume of a system. So your H, your enthalpy is equivalent to E. Okay, your H enthalpy is equivalent to the internal energy. Okay, S is your entropy. Entropy is nothing but a measure of unavailable energy in a system. Okay, it's a properties. It's not a measurement. Okay, it's a measurement of randomness of a system. Okay, it's a property of randomness of a system. We can call that as unavailable energy. Okay. Now, at constant temperature and pressure at fixed PV, a closed system which is have a fixed mass and composition will be in stable equilibrium if it has the lowest G. Okay, if it has the lowest free energy or rate of change of G is equivalent to 0. Okay, please remember this. At constant temperature and pressure, a closed system will be in stable equilibrium if it has the lowest G, right? So a material is stable, we can call that in a stable equilibrium when the Gibbs free energy is at the lowest state, right? So there is no growth of nuclei. So everything is stable. It is in the solid form. Okay. Now let's move on. So this is your Gibbs free energy equation. G is equal to H. H is your enthalpy minus with Ts. T is your absolute temperature. S is entropy. Now, the state with highest stability, highlight this, the state with highest stability is the best compromise between low enthalpy and high entropy. Okay, let's look into two different types of phase. At low temperature, solid phase most stable. Okay, it has the lowest E. E is for the potential energy, internal energy, which is low, and H is the enthalpy, is lowest. So that is due to the low temperature. Solid phase is more stable, strongest atomic bonding. Okay, just imagine in a solid, all the atom is being bonded together strongly. So it is in a stable phase. So during stable phase, you have the lowest internal energy and enthalpy. At high temperature, Ts dominates. Okay, your entropy dominates, where phases with more freedom of atom movement, liquid and gas, is more stable. Okay. Now, let's look at the Gibbs free energy. Okay, this is the Gibbs free energy chart and arrangement of atom. Okay. Here, you have a rate of change of D 0, here 0. So this means that at the present arrangement of atom, here is the slowest state. Okay, configuration A, let's look at configuration A, has the lowest free energy. Okay, lowest free energy from the Gibbs free energy, and is therefore the arrangement when the system is at stable equilibrium. All right, here configuration B has an energy higher than configuration A, therefore configuration B is at metastable equilibrium, not stable. Right. Please take note of this. So that is about where am I? Gibbs free energy system. Points to take note is condensed phase, liquid and solid, PV terms is small in comparison to E, where your H is equal to your internal energy, sorry, your enthalpy is equal to your internal energy. And in your S, in Gibbs free energy system, S terms as entropy is a measure of randomness of a system. And this is the thing to take note. At constant temperature and pressure, a closed system will be in stable equilibrium if it has the lowest G. Okay. And then from the same Gibbs energy, free energy formula, the state with highest stability is best compromise between low enthalpy and high entropy. Okay, at low temperature, solid phase most stable. Okay, you know that, right? Because of strongest atomic bonding, it has the lowest E. E is for internal energy, and H is the enthalpy, sorry. At high temperature, the domination is more on the TS, phase with more freedom of atom movement, which suggests that it is more stable. Okay. Now, having said that, you have two types of mechanism for the creation of nuclei. Right? The two main mechanism of nucleation of solid particles in liquid metal is homogeneous and heterogeneous. Please highlight these, homogeneous and heterogeneous. Okay, there's one question. Why must be the entropy to be high? Where is it? Enthalpy must be high, not entropy. Enthalpy. Nur Harpinder. Enthalpy must be high. Okay, low enthalpy and high entropy. Or wait, Nur Harpinder, which one are you quoting? Which slide? Slide 7. Let me have a look on that. Oh, okay, for the stability. All right, best compromise between low enthalpy and high entropy. All right, at low temperature, all the metals, okay, the material, okay, we are talking about metals, right? At a stable state, right? So once the material are in stable state, its entropy is high and the enthalpy is lower. Okay, so basically, in general term, when a metal are in solid form, all the atoms are in equilibrium state, where there is no any growth of nuclei. All the nuclei are in stable grain form. Okay, stable crystal grain form. Okay, that is the reason why the entropy is high, and on the stability they said that the best stability is achieved when there is a term on low enthalpy and high entropy. Okay, this is being discussed here. Here, at low temperature, solid phase is more stable due to the strongest atomic bonding, where it has the lowest internal energy and also lowest enthalpy. Okay. Next, wouldn't the entropy reduced when the metal cool down, or it is because it can be reversed and therefore the entropy increase? Let me try to digest your question. Wouldn't the entropy reduced when the metal cool down, or it is because it can't be reversed, therefore the entropy will increase? Okay, entropy is a properties. Okay, it's a measurement of it's a measurement of system disorder. All right, so the changes of entropy can be reversed when there is a sufficient temperature that can increase the free energy in a system. Okay. Entropy can be reversed if there is a sufficient energy in a system due to the increase in temperature, and therefore increases the Gibbs energy, free energy. Okay. Next, what is the significance of being metastable? Configuration B in slide 8. All I know is the find of a second derivative of G0. Second derivative of 0. Okay, what is the significance of being metastable? Configuration B in slide 8. Let me see that. Okay, you have arrangement of atom in slide B. Okay, metastable. They said metastable is because the material is. Wait a minute. The material tends to become metastable when there is a energy increment in an atom so that it disrupts the arrangement of atom and the atom starts to flow freely. So that is the meaning of metastable. It means that disturbance of, how do I put in word? It has excitation on an atom so that it is theoretically unstable. Okay, it is theoretically unstable that creates a disturbance within the region of an atom. Okay, Lua Wen Zheng. All right. Harpinder, are you okay? Nur Harpinder. Okay. Okay, guys. Now, where am I? Okay, formation of a stable nuclei in liquid metal. Okay, as I mentioned to you, we're going to quote metals. So there are two types of mechanism involving nucleation in solid. The first one is homogeneous, and the second one is heterogeneous. Highlight this. Now, as a rule of thumb, homogeneous is rarely happens. Okay, homogeneous rarely happen in practical term. Heterogeneous is what happens in nature. Okay, not to say in nature. Let's talk about heat treatment. Okay, in heat treatment process, all the process is being driven by heterogeneous mechanism to solidify a metal. That is the reason why they use, if you read about steel works, okay, if you read about steel works, they add calcium carbonate. Calcium carbonate act as a nuclei agent. Okay, I'll discuss with this with you later towards the end of this slide. Okay, so as a general term, most of the mechanism of nucleation is happening on the scale of, on the understanding or on the principle of heterogeneous. Okay, homogeneous is rare. Okay, now let's talk about homogeneous first. Homogeneous nucleation in a liquid melt occurs when metal itself provides atom to form nuclei. Okay, I'm repeating this again. Homogeneous nucleation in a liquid melt occurs when the metal itself provides atom to form a nuclei. So usually homogeneous happens in a pure metal, pure 100% pure metal, and there is an effects of undercooling. Okay, undercooling is equivalent to supercooling. Okay, supercooling. Where the definition of supercooling is, or undercooling, where you don't have sufficient, the temperature is too low, where the material doesn't have sufficient time to create nucleus. Okay, it takes some time to create nucleus. All right, so it stays on a liquid form for a longer period of time, for a temporal period of time. Okay, so nuclei on the new phase form uniformly through the parent phase. Okay, here you go, pure liquid metal. When pure liquid metal significantly undercooled, okay, yeah, this is the one that I'm trying to say. And highlight these. When pure liquid metal significantly undercooled, several slow-moving atoms bond each other to form a nuclei. Remember, guys, these are temporal adjustment of the atom on the system itself. Okay. Next, nucleus stable grow into crystal. It must reach a critical size. Okay, this is the phase of homogeneous nucleation. The process of homogeneous nucleation. Nucleus stable grow into crystal. It must reach the critical size. Okay, when the clusters of atom couldn't reach critical size, or when the clusters of atom below the critical size, we call that as embryo. When the clusters of atom, the outcome, I'm talking about the outcome, when the clusters of atom reach critical size, they grow into crystals. So for an atom to reach critical size or not, it depends on the free energy, G, Gibbs free energy. Okay, there will be several formula will be discussed after this slide, so you can have a better understanding on it. So I'm repeating this again. You have two outcomes. When the nucleus grow into crystal, it must reach a critical size. Okay, it must reach a critical size. And when the cluster of atoms is below the critical size, it is called embryo. And if the cluster of atom reach critical size, they grow into crystal and followed by grains. Or else they get dissolved. The nuclei get dissolved and repeat the same process again until it attains sufficient energy. Okay, so there is an opposing energy to Gibbs free energy. We call that as surface energy, surface free energy. Okay, you can write it down first, surface free energy. Now, clusters of atoms that are greater than the critical size are called nucleus. So now your focus must be on the critical size. Okay, so I'm going to discuss with you critical size in terms of critical radius, because all the atoms are depicted to be sphere. So critical size, I'm going to discuss with you in terms of critical radius. Okay. All right. Now, energy involved in homogeneous nucleus. So I want you to memorize two types of energy. The one is GV. We call that as bulk free energy or volume free energy. Another one is GS, is the surface energy or surface free energy. Okay, so you have GV and GS. So energies involved in a homogeneous nucleation, two energies changes must be considered. The first one is the volume or bulk free energy. And this volume energy is released by the liquid to solid transformation. Energy is being released by the liquid to solid transformation. Remember, when solid becomes liquid, energy is being absorbed. Okay, when liquid becomes solid, energy is released, so it is released by the liquid solid transformation, and this is the opposing force. Number two, the surface energy GS required to form the new solid surface of the solidified particles. I'm repeating this again. The surface energy, Gs, required to form the new solid surface of the solidified particles. So you need to attain energy higher than Gs for you to come up with the critical radius. Okay, now let's talk about volume free energy, GV. Okay, GV is the driving energy for liquid to solid transformation. Okay, it is the difference in the volume free energy of the liquid and that of solid. Okay, GV is the difference in the volume free energy of liquid and that of solid, okay, and the energy is released, and the changes of GV is the change in free energy per unit volume between liquid and solid. For example, you have a solid here and you have liquid here. Okay, this is your radius. Surface energy concentrate on the area. Volume energy concentrate on the volume. All these happens in the solid liquid interface. Okay, here free energy change for spherical nucleus of radius is given by this. Okay, this is the formula, you can just memorize this. Now surface energy. Surface energy is the energy opposes to the formation of embryos and nuclei. Highlight this. Surface energy is the energy opposes the formation of embryos and nuclei. The energy to form the surface of these particles. Okay, and changes of Gs is the energy required to form new solid surface. And then you have another term, we call that as gamma. Gamma is the specific surface free energy of particles. So whenever there's a question on this, I'll be giving you gamma. All right. Then Gs is equal to the specific surface free energy of the particle gamma times with the area of the surface of the sphere. Gamma times with the area of the surface of sphere. Okay. So surface energy is a retarding energy, which is a delayed energy. Okay, is a delayed energy. Essentially, surface energy opposes the formation of embryos and nucleus. Okay, guys, try to digest GV and GS. Try to digest GV and GS before I move into a more in-depth analysis. Okay, I'll give you time. Let's take a break. I'll give you time for until 2:50. Okay, I'll give you time until 2:50. Try to digest until what I've taught you, and then we continue with homogeneous nucleus. Okay. Try to digest first. Let me know if you have any questions. Okay, guys. All right. Give me one question. Lo and Zheng. Okay. GV is higher than GS. In order for nuclei to achieve critical size to form crystals, just to reconfirm again. Okay, now for this question, okay, if you look at this, can you see slide 14? Guys, can you hear me? Okay, can you see slide 14? All right, good. Okay, if you look at slide 14, okay, this is your GS and this is your GV. In order for the material to form nuclei and for the transformation to take place, your GV, once it reaches the critical nucleus, this R asterisk is critical nucleus, okay, it needs to follow GV. So this is your surface opposing force. This is your GV. So before it reaches critical radius is when your GT following the values of GV. So the transformation will only occur when the sum of GS and GV becomes negative. So another way of saying it is, where's the question? Yes, GV should pose higher values for than GS so that a transformation of nuclei takes place. Okay, so this is the radius of particle. Okay, this is the radius of particle. Below it, this is embryo, and here it just solidify again. Above it, nucleus tends to grow, becomes grain. The radius particle increases. Okay. So from this, can you understand clearly? Lua Wenzheng. All right, that's good. So the total free energy to form an embryo or nucleus, okay, embryo or nucleus. This is the total free energy. Okay, the magnitude of GS and GV. Okay, and your critical radius is -2 gamma is the specific surface free energy divided by your GV. All right, so this is your critical radius. For radius, below the critical radius, the nuclei shrink and dissolves. For radius, nuclei radius, above the critical radius, it's tend to grow and transformation takes place. So the magnitude of GT follows the magnitude of GV. So then only the transformation will occur. So therefore, before even the transformation takes place, the negative term GV must be greater than the positive term GS. Okay. All right. So guys, just take note of this. Total free energy. You have GS, you have GV, and you have GT. Okay. So nucleus above critical radius, energy lowered by growing into crystals. Okay. Energy lowered. Can you see the word here? Lowered by growing into crystals. So energy is being released, right? And below critical radius, energy is lowered by redissolving, and it attains back the energy until it goes back to critical radius. Okay. Now, so I've discussed about GV. Now, GV depends on the temperature. The magnitude of GV the magnitude of GV depends on temperature. So the magnitude of GV depends on latent heat fusion, okay, HF, your melting temperature, absolute melting temperature, minus with the present temperature over temperature. So with lower temperature, okay, if you have a low temperature, both G and critical radius decreases accordingly. Okay, so this is higher temperature T1, T2 is lower temperature. So the critical radius for lower temperature is lower, critical radius for higher temperature is higher. And the change of your energy is larger for higher temperature and lower for lower temperature. Okay. Now, critical radius and undercooling. Okay, let's see this. Greater degree of undercooling, greater change in volume free energy. Highlight this. This is the statement. The greater the supercooling, undercooling, the greater the change in volume of free energy. And it doesn't affect GS, the surface energy, because surface energy does not change significantly with temperature. Surface energy depends on the surface area of the atom. Therefore, as the amount of undercooling increase, critical nucleus size decreases. And the relation is being drawn here. Okay, the relation is being drawn here. Is it okay? Right. Okay, critical radius is related to undercooling by the relation of this. Okay, critical radius, and gamma is your surface free energy. Change of half is latent heat fusion. Delta T is the amount of undercoolings. Right. Next, let's talk about a bit on supercooling. What is undercooling is all about. So supercooling, as I mentioned to you earlier, is a phenomenon during the cooling of a liquid, an appreciable nucleation rate. Okay, solidification will begin only after temperature have been lowered to below the equilibrium solidification or melting temperature. Okay, in other words, supercooling is the temperature at which a temporal adjustment of temperature which is way below the melting temperature, and it restricts the formation of nucleus temporarily so that the liquid stays in liquid, so that the metal stays in liquid formation. Okay, so for example, you have your freezing temperature 600, your maximum undercooling temperature is 80, way below the freezing temperature. Okay, copper 1356, your maximum undercooling can be 236. Okay, just an what they call that, a definition for you. So that's on homogeneous nucleation. Now let's talk about heterogeneous nucleation. Okay, now in practical situation, a large amount of undercooling is unlikely to occur for homogeneous nucleation because undercooling requires a lot of energy. Right? In a practical situation, a large amount of undercooling is unlikely to occur for homogeneous nucleation. So nucleation occurs in a liquid on the surface of its container. There's a lot of insoluble impurities, grain boundaries, dislocation, and other structural material. Okay, we can call that as nucleating agents, which I mentioned to you earlier in this lesson. Nucleating agent, calcium carbonate. This can, okay, all these process can lower the critical free energy required to form a stable nucleus. All right. So heterogeneous nucleation is nuclei form preferentially at the surface in homogeneities. So in practical, most of the material are not in pure form. Most of the material are in alloy form, or you have some impurities in the material. Okay, impurities in the metal. Okay, all the metals are not in pure form. You have some impurities. So during solidification process, instead of homogeneous nucleation, heterogeneous nucleation process takes place, because homogeneous nucleation takes place during undercooling, and undercooling requires a lot of energy. Heterogeneous nucleation is a nuclei form preferentially at the structural inhomogeneities, and this having a factor on the insoluble impurities. It has a factor on grain boundaries, dislocation, and other structural materials, for example, nucleating agents. And all these factors has the tendency to lower the critical free energy required to form a stable nucleus. Okay, for this lecture, I'm going to focus on nucleating agents. Okay, this is another new broad topic, but just for the sake of simplicity, I'm going to discuss on nucleating agents. Okay, here, since the surface energy is lower, okay, because of all these factors, the total free energy change for the formation of a stable nucleus will be lower, and the critical size will be smaller. The critical radius will be smaller. Therefore, small amount of undercooling is required, not large amount. A small amount of undercooling is required to solidify to form a stable nucleus. And this process is used extensively in industries in terms of heat treatment. Okay. Now let's look into heterogeneous nucleation. For the heterogeneous nucleation to take place, a solid nucleating agent must be wetted by the liquid metal. For example, you want to increase the solidifying process in a molten steel. Okay, if you look into a large scale industries, for example, bulk, where let's talk about 100 tons of liquid metal to be solidified into solid, they use a nucleating agent, for example, calcium carbonate. Okay, so this calcium carbonate must be wetted by the liquid metal by pouring into it. The liquid should solidify easily on the nucleating agent. So if you look at the figure here, this is your nucleating agent, and this is your liquid metal. Heterogeneous nucleation takes on the formation on the surface of nucleating agent. Okay, nucleating agent wetted by solidifying liquid, creating a low contact angle between the solid metal and the liquidating agent. So you have a contact angle here. And this is your solid surface. This is your solid liquid surface on the surface of solid and liquid, solid liquid surface. And this is your liquid surface energies. Okay. The energy barrier, okay, the energy barrier here for heterogeneous nucleation is relatively lower than that of homogeneous nucleation due to reduced of surface free energy. this surface free energy is being reduced from the nucleating agent. Okay, so if you look at heterogeneous energy barrier is lower than homogeneous energy barrier, which is higher. Okay, so the heterogeneous energy barrier is smaller than the homogeneous energy barrier by an amount corresponding to the value of S. You have an angle, right, theta, where S theta is the function of solid liquid tangential angle which have a value between 0 and 1. Okay, and let's talk about growth of crystal formation of the grain structure. Nucleus growth into crystal in different orientation. Okay, random orientation. Crystal boundaries are formed when the crystal joins together at complete solidification, where you have grain boundaries. Okay, the boundary between two nucleus becomes smaller and you have grain boundaries. Crystal in solidified metals are called grains. Okay, crystal in solidified metals are called grains. And the grains are separated by the grain boundaries. Right? More the number of nucleation sites available, the more number of grains form. Okay, this is in PDF format. Are you seeing in PTT PowerPoint format or PDF? Okay, if it is in PowerPoint, oh, in PDF. Okay, hold on. I see on paper. Oh, okay? You have printed it. Okay, all right. All right, just hold on a second. Let me open the PowerPoint. Essentially, what you see is a growth of crystal. That's all. Okay, it is just a repetition of this slide. This slide growth, and it becomes this. Okay, hold on, guys. Hold on. Just give me a second. Okay. Let me share you my PDF, my PPT. Okay, can you view, guys? Can you view this? Okay. How about now? Can you view? Can you see the animation? Nuclei growing into grains, forming a grain boundaries. Okay. All right. Hold on. Okay. How about now? Can you view now? Nuclei growing into grains, forming a grain boundaries. All right. So this is just an animation. So more the number of nucleation sites where the transformation takes place after the energy goes into its critical energy, the more number of grains being formed, and the crystal increases in size, and there's a formation of grain boundaries. And there you go, you have the grain boundaries. Then it solidifies. Okay. Okay, guys. So so types of grains. All right, there are two types of grain. One is equiaxed grains, where the grains which is smaller than columnar grains, but equiaxed grains grows equally in all directions. Okay, you just need to memorize these grows equally in all directions, and it form at the sites of high concentration of nuclei. Okay, equiaxed grain form in a high concentration of nuclei. For example, cold mold wall, okay, on the walls of cold mold and on the high concentration of nuclei. Okay, you have another one, another types of grain, which is columnar grain. Columnar grain is a long, thin and coarse grain which is almost perpendicular to the surface of mold. So it is perpendicular due to the higher steep temperature gradient. So columnar grain occurs formed at the site of slow cooling and steep temperature gradient. So here is more cooling, here is more hot. It grows in that direction in a steep temperature gradient. Okay, and it grows predominantly in one direction. It is long, thin and coarse. For example, grains that are away from the mold wall. Okay, equiaxed grain grows equally in all direction, form at the sites for high concentration of nuclei and in a more colder region here. Okay, so guys, I'm going to repeat today's lesson. Okay, solidifications. Two steps involving in solidification. The first one is nucleation, formation of a stabilized nuclei in the melt, and the growth of nuclei into crystals, and this crystal form grain structures. Okay, you have nuclei, and the growth of nuclei when you have sufficient energy, it grows into crystal, and this crystal grows into grains where you have grain boundaries, right? And phase stability, all this system is governed by the Gibbs free energy, where G is equal to H enthalpy minus Ts, absolute temperature and entropy. And enthalpy is the measurement of heat content. H is equals to internal energy plus V, your PV, pressure and volume. And okay, yeah, at constant temperature and pressure in a closed system, it will be in a stable equilibrium if it has the lowest G. Okay, a phase molten metal will be in a stable equilibrium if it has the lowest G. And here at low temperature, solid phase are in most stable due to the lowest E and H, internal energy and enthalpy. At high temperature, Ts is being dominated because phases have more freedom or atom movement. Okay. And in phase stability, configuration A has the lowest free energy, and therefore the arrangement between when the system is at stable equilibrium, and B is in metastable, energy is higher, energy is lower, stable. And the formation of nuclei in liquid metal, there are two types of formation of nuclei. The first one is homogeneous, the second one is heterogeneous. For homogeneous, it is very rare and involve undercooling, massive amount of undercoolings, supercoolings. And we have another one which is heterogeneous. which is commonly occurred during heat treatment. All right, for homogeneous, when pure metals, pure, okay, the word is pure, is significantly undercooled, several slow-moving atoms bond each other to form a nuclei. Okay, so now you know how it moves slow because you are on a critical temperature. Okay, when you reduce the temperature, the atom tend to have lower energy levels and it starts to move slow. Once it starts to move slow, it releases energy, and slow moving atom can bond each other to form a nuclei. That's the reason why metal itself provides atom to form nuclei. Okay, sorry. And a nucleus stable grow into crystal, it must reach critical size. Okay, this can be size. This can be depicted in this slide number 14. And the clusters of atom below the critical size is called embryo. And if the cluster of atom reach critical size, they grow into crystal, or else it dissolves back into liquid form. Clusters of atom that are greater than critical size are called nucleus, and it grows into grain crystals, then it goes into grain. So within all this process, the energy involved in homogeneous nucleation is two. One is the free energy GV, and another one is the surface energy GS. GS is the opposing energy. Right? GV is released by the liquid to solid transformation. So this is GV. Surface energy opposes the formation of embryos and nucleus. Is the energy required to form new solid surface, and you have a new what they call that terms, gamma, which is the specific surface free energy of a particle. And surface energy is not influenced by temperature. Surface energy is influenced by the surface area of the particle. Here, in order the formation to take place, transformation to take place, GT must follow GV, okay, where the magnitude of GV must be higher than the magnitude of GS. All right, so GT is the plus of GV and GS, and this is your critical radius. Atom below the critical radius, you have predominantly by GS, it will never reach nucleation. Atoms above the critical radius, predominantly dominated by GV, will eventually turn into crystal and what they call that grains. Okay, and the magnitude of GV depends on temperature. Okay, this is the formula. Critical radius and undercooling, this is just an what they call that site information for you, and supercooling as well. Heterogeneous nucleation occurs in a liquid of the surface of its container. Insoluble impurities, grain boundaries, dislocation, and other structural material nucleating agents that lowers the critical free energy required to form a stable nucleus. The factors, and also the places where nucleus being formed. For this slide, I'll be focusing on nucleation agents. Since the free surface energy is lower, the total free energy change for the formation of stable nucleus will be lower, and the critical size will be smaller. Right? For example, in a molten metal industry, okay, metal industry where you have a bulk metal, where in the molten metal, the engineer will be pouring a nucleating agent, which is calcium carbonate. Okay, so on the surface of calcium carbonate, nucleation takes place in terms of heterogeneous nucleation, and it starts to grow. All right, and the energy barrier for heterogeneous nucleation is relatively lower than that of homogeneous nucleation due to reduced surface energy. Then we discuss about the growth of crystal and the formation of grain structures, how the crystal grows from atom. Once it reaches critical energy, critical radius or critical size, it becomes crystals. It grows bigger. It grows bigger. Okay, so once it grows bigger, you tend to have an grain boundaries. So attain to have grain boundaries, and it causes the whole thing become solid. So more numbers of nucleation sites available, the more numbers of grain being formed. And then the types of grains. We have two types of grain. One is equiax grain, where equiax grains are smaller in size and act on all the direction. Okay, grows equally. Yeah, grows equally in all directions, and form at the sites of high concentration of the nuclei. Example, cold mold wall, and also at the center. And columnar grains, which is long, thin, and coarse, which is almost perpendicular to the surface of the mold. It grows perpendicular because it grows towards the steep temperature gradient from colder region to hotter region. Okay, for example, grains that are away from the mold wall. Right? Why the surface energy is lower for heterogeneous nucleation? Okay, the surface energy is lower for heterogeneous nucleation because you have a catalyst. For example, the catalyst here that I'm talking about is these nucleating agents. Okay, those are chemical catalysts. We call that as nucleating agent. No problem. Okay. So guys, on this Friday, I'll start off with kinetics of solid state transformation, which is just a few slides. And then just a quick ramp before we start up with our tutorial. Okay. And after this class, I'll be uploading tutorial 2 questions in Webull, so you can try it out. So tutorial 2 questions has lecture 3 and a part of lecture 4 as well. Okay. The catalyst has a smaller gamma value. Where is it? Interfacial energies. Smaller gamma value. Why would that? I'm not sure on that. The catalyst has smaller gamma value. Yeah, it should be. I mean, by logic, yes, it should have a smaller gamma value. Because the energy barrier is relatively smaller than homogeneous energy barrier due to the reduce of free surface energy. Yeah. Yes. Chinwai, look. Okay, guys. So I will be uploading the what they call that. Okay, I need to stop recording. All right, guys, I'll be uploading the tutorial 2 later.